Okay, so today is Monday, October 12th. And today we're going to start on constrained optimization, which hopefully you've looked at the notes, read the notes. As I emphasized in the past, just read them, just read through them and get the general feeling, okay? If there's details you don't understand, that's fine. But if you just read it, I think it'll help get your head in the right space. And you can go back and reread, okay? But constrained optimization is pretty cool and super crazy in a way. Okay, so here is the deal. So constrained optimization is going to turn out to be a key tool, something of growing importance. It's really become kind of a hot strategy, a hot topic in the last I would say 10 years, okay? It's always a little bit fuzzy, of course, with these things. And constrained optimization has been around for 100 years, okay? But it's become kind of hot in this field in the last 10 years. And it's essentially a different way of sort of slicing and dicing your problem up that turns out to be very useful. So it's a little bit like, philosophically, it's not technically like, but it's philosophically like the constrained optimization, like the surrogate functions, because the surrogate functions are sort of a general class of techniques that you can use. It's sort of like a tool, right? It's like you go to a hardware store and you get like some kind of Swiss Army knife thing that's like got 27 things that pops up on it. And it's like a particular kind of tool that's particularly handy for these problems. It's the same thing with the constrained optimization, but in a completely different way. It's a different collection of tools. So it's not just one thing, okay? It's really a sort of a collection of things, okay? So that means that, you really have to understand it in order to be able to use it. And it's super counterintuitive because it seems like you're doing exactly the wrong thing, okay? And somehow it works out to be useful. So here's how it works. You're often solving a problem, and by now maybe you believe that many of these problems have the following form, okay? You have to solve some problem like this. In fact, it can even be worse than that, or better, or depending upon your point of view. It might be that you have an f of x, which is equal to the sum from, say, I equals 1 to n of fi of x, or 0 to n minus 1, say. So you have a function you're trying to minimize, which is formed by a sum of functions, okay? But 2 is the small, 1 is obviously no different, it's not very interesting. So 2 is the first case that's interesting, right? N we'll get to later, but for now we'll just worry about 2, okay? So the problem is this, that if you were trying to minimize f of x, you might, okay, one thing hopefully you learned is that different functions require different, assuming these are both convex, in fact, okay? So they're very well behaved, they're convex. But different functions require different optimization techniques. So different kinds of strategies, right? So you don't want to use the same strategy to solve this as you use to solve that, okay? So the problem is that you're trying to do these together, right? It's like you have, it's like you can't customize, right? So you have like 2 people, you're serving them dinner. This is a really bad analogy, but that's the price you pay for having a class with me. That you have like 2 people at dinner, and one, only likes to eat one kind of food, and the other only likes to eat the other kind of food, and you can't make them both happy, okay? So you really want to try to make them both happy. You want to do things you want to do the optimization. The most classic example of that is that, let's say f of x is something like 1/2 the norm of y minus ax squared, okay? And let's say g or h of x, is something like an L1 norm of some transformation of x. This is, you can write total variation regularization. This could be like TV. You say, well, this doesn't look like TV, because this matrix here could be a matrix that just takes pairwise differences between adjacent pixels. And then the L1 norm, everybody knows what an L1 norm is, right? It just sums the absolute value. So this would be like the sum of the absolute value of the differences between adjacent pixels, okay? So this is convex, this is convex, this is, if A is full rank, then this is going to be strictly convex. But this is not strictly convex, right? Because the absolute value function looks like that, which is not strictly convex. And this is not continuously differentiable. So you really can't, technically speaking, you can't use gradient descent. Or at least if you do use gradient descent, it won't get you to the global minimum. It won't even vary. I mean, technically you can't use gradient descent because the gradient doesn't exist. You say, well, the gradient exists almost everywhere. Yeah, but the points where you're going to hit points where you're going to be at those vertices because of this issue that if you drop a polytope, it hits the ground, it hits a table, the corner's going to hit first. So you always hit those vertices. The vertices aren't insignificant. You'll hit them all the time. And when you hit them, you can't differentiate the function there. Well, you can say, well, okay, I'm an engineer. I'm going to make some approximations. Okay, but it's a problem. You really can't do gradient descent with this function. Okay? In any case, the functions behave very differently. If this is topography, this is like an integral relationship, and this is a differential relationship. That means that the eigenvalues are going to be, the eigenvalues that are large here will be small there. So they're just very different natures to them. So the problem here is that you're trying to do this optimization, and you have to minimize both together, that it's a problem, because they behave very differently. So instead what you do is you do something which seems like a crazy idea, okay? You do this. You say, what I'm going to do instead is I'm going to take the argmin. I'll break the two functions up. I'll have f of x plus h of v. And I'll minimize over x and v together. Okay, now if you do that, obviously you're just getting the answer to a different problem. So why would you do that? Well, I'm going to add an additional constraint subject to x equals v. Okay, which is, so then now that's this, okay? Now this seems like a crazy thing to do, because what you've done, you've doubled the size of the dimension of your optimization problem, and you've turned an unconstrained optimization problem into a constrained optimization problem. And if you do any constrained optimization, generally the feeling is that when you're, like if you learned about constrained optimization as an undergraduate or whatever, most of the time you're trying to take constrained optimization problems and turn them into unconstrained ones, because you know how to solve unconstrained problems and you don't know how to solve the constrained problems. So it seems like just a horrible idea. You've doubled the size of your problem and you made it harder, okay? And you made the problem that was double the size harder. It seems like a terrible idea, okay? Okay, but bear with me, because it's going to turn out that it's actually very useful. And the reason it's useful is it decouples the optimization strategies for the two functions. So you can use different techniques, okay? And you can customize them to the individual functions, okay? So, okay. So everybody gets this, right? The next thing I'm going to do, okay, hold on. I'm going to basically tell you the answer. So this is subtle. So make sure if you get to a point where I'm saying something and you don't feel clear about it, just ask me, because any question you have, somebody else in the room will have. Okay? So now how are we going to do this, okay? So the way we're going to do it was say, okay, we'll do an argmin over x and v of, we'll say f of x plus h of, h of v, and then plus, hold on for a second, I want to make sure I use the same notation that I use here. Yeah, okay. Plus a over 2, okay, times x minus v squared. So what did I use this? Okay, I use this term because we have like x, we have x, we have some point, this is sort of the x-axis, so you have, this is x, and this is v. Okay? If I do the optimization of x and v separately, they're each going to go to whatever their minimum is. Okay? But instead what I do is I say, okay, well, I'm going to take a spring, and I'm going to connect them with a spring. Now, the problem with the physical analogy of the spring is the spring has its own physical distance. But imagine you had a physical spring where it was designed so the two ends of the spring started in the same location at rest. Okay, so that the spring had no length to it. So then, so the spring would pull the 2 points back together. Okay, and this is the equation for the energy of a spring, if you recall, because the force for a conventional linear spring, the restoring force is proportional to the displacement of the spring. So the integral, so that means that the restoring force is minus x, and if you integrate x, you get like x squared over 2 or times 2 or something like that, right? Yeah, you get x squared over 2, because if you differentiate it. So this is, A is the spring constant. Okay? Spring constant A. By the way, I should tell you, maybe you know this already, I'm a very geometric, physical thinker. So for these equations, I really always think of these equations in terms of their physical analogy. Some people just manipulate the equations directly. They're more purely algebraic, but I like to think of it in terms of the physical meaning, okay? All right, so the idea is that if you make this spring taut enough, right? If you make this spring, if you take the limit as a goes to infinity, what's going to happen? As the spring constant, as the spring becomes stiffer and stiffer and stiffer, right? What's going to happen? Yeah, excuse me? Well, you'll expect that, by saying there's a delta function, what does that mean in terms of x and v at the solution? Yeah, it's going to be, So let me draw it, actually, because to help give you some physical intuition. So this might be f of x. Obviously, these are usually multidimensional functions, but the one-dimensional case, it tells you what pretty much the deal. Okay? And then this is going to be h of x, right? Right? But now what will happen is that it's hard to draw the other function because it's not just a function of x, it's a function of x and v, right? So what will end up happening, so this would be like, this is like the x-v axis or something like that, right? And it's saying, oh, well, but I have a cost function that if x and v aren't the same, then there's going to be a huge increase, okay? So maybe the better way to describe it is sort of like, maybe I could draw it like this. I'm sort of making this up as like, so this would be like x, and this is v, right? So what will end up happening is that there's some function here, like this is f of x, and over here, this is something like, I don't know, this is h of v, right? And now what happens is there's a function along here that's really steep, okay, that strongly penalizes you for not falling along this line, right? So it's going to find a point where, okay, there and maybe there, where the two things, the sum of the two things balances, okay? But it's not the minimum of either individual one. It's the minimum of their sum plus this additional constant. Okay, but the additional constant is a really strong force, okay, that if they're not equal. But what will end up happening is this is x hat, and this is v hat. V hat and x hat, v hat will not equal x hat, generally speaking, because no matter how big that spring is, you'll pull it a little bit, it'll be a little bit off, okay? Now you'd say, well, from an engineering perspective, it's good enough. I'll just make A really big, okay? And then that'll be close enough. The two V and X at the solution will be close, okay? Are people following this? Because it is important to get this or you'll get confused at the next step I have to make. Is there anybody who wants to ask a question? You'd be doing everyone a favor if you have any thoughts or comments or anything about this. Does this make total sense? Do you get this? The idea you're minimizing now the sum of these two functions plus a function which penalizes the difference. And A is the spring constant, so as A goes to infinity, these will get closer and closer together. But for any finite A, it will never actually give you the exact solution to your original problem. It'll just give you an approximation, okay? Does that make sense? Okay, good. So you got that set. Now, here's the problem. As A goes to infinity, problem becomes stiff. Stiff optimization problems are hard to solve. Has anybody ever heard that term before? For like when you're solving a PDE and your PDE is stiff, okay? You may have like boundary conditions. Some PDEs will be stiff and they're hard to solve, okay? Which is really weird because when a problem's stiff, it should be easier to solve because, for instance, you make a problem will be stiff if like you have hard constraints that certain points in the PDE have to be equal to certain values. And the reason is that it's stiff because it's like you can't move that point. And the problem is that it's really hard to solve those problems because you can't, like you're trying to move the stuff around and it sticks, okay? It'd be like, I'm trying to remember, I don't know what an analogy would be, but like, you know, there used to be these little puzzles where you'd like slide the pieces around to get like the pattern to come out right. And like, if they were like, they had to have grease on them, but if they didn't have enough grease on them because you got them out of a Cracker Jack box and you couldn't move them, so you put a little bit of grease on them and then you can move them around, right? The problem here is that as A becomes infinity, here's the technical, okay, that's the physical analogy. Here's the technical statement. As A goes to infinity, this problem becomes ill-conditioned. What do I mean by ill-conditioned? Did I tell you what the conditioning number was? I don't know if I ever told you the conditioning number. When you're trying to solve a problem, the conditioning number is the ratio of the largest to the smallest singular value. So the ratio of the largest to the smallest singular value goes to infinity as A goes to infinity. So the problem becomes, so we saw with gradient descent, gradient descent doesn't behave well when the conditioning number is poor. So this thing becomes stiff, the conditioning number is poor, it's hard to solve it. Yeah?
So essentially it doesn't want to change from its initial.
Yes, I mean, here's one way of thinking about it. Let's say you set V. You can't move X. Here's another way of thinking about it. So you can't move X, how are you supposed to solve? Here's another way of thinking about it. your solution needs to fall on this constraint space, okay? So, but you're trying to solve your problem. Now, what ends up happening is if x and v are high-dimensional vectors, this is actually a linear subspace in the higher dimensional space, okay? It's a linear manifold in the higher dimensional space. And what happens is that you can't move off this. Let's say that you start here, okay? But the answer is there. You need to get from here to there, right? Well, you might go like this and then go like that, but you're not allowed to do that because you cannot move off that space, because if you do, the cost goes up horribly, right? It's like you have to get from here to there, but you have to stay exactly on this line. And if you like walk to the off the line a little bit, like, I don't know, some horrible thing happens to you, okay? Okay, it's like Star Wars in a giant weight, like when Bugs Bunny falls on you, boom. Okay, so you're like boom. Okay, every time you go, stop it! I'm just trying to walk from here to there. I promise when I get there. So if you're like me, you're like, oh, I'll just like walk like this over here, and then I come over here. Okay, the point is this. This is what the administration wants you to do. Okay, they want you to live right along here. You know, they're watching you all the time. Okay, and you're like, leave me alone. Just look the other way for just a moment. Okay, okay. So the idea here is that, okay, I know, I gotta enforce the constraint. I heard you already. Okay, stop nagging me. Okay, I know I want to get here. Just let me alone and I'll be fine. I'm going to go over here and I promise I'll come back, okay? So the mathematics of this is, yes, I know I have to enforce this constraint, but I don't need to make this thing infinite. You know, just let me get over here, and when I get there, I promise I will home into the solution, okay? Yeah?
Is this what people mean when they talk about relaxations of problems? This would be like a relaxation of our original optimization problem?
Yes, it is an example of a relaxation, but some people just like relax the problem and solve an approximate problem. In this class, we're too pure for that, okay? So I'm going to give you a solution to the exact problem, but it's going to be based upon a philosophy of cheating, okay? Okay? So the idea is that, well, we kind of are a little bit sloppy. We come over here. We don't worry about it too much. But when we're all finished, we make sure it's right. Okay? And how is that going to work? Okay, so I'm getting you the story. Okay, so you got this. You know what that is, right? You got this, which is this crazy thing that seems to make no sense. Okay? That you made it a lot harder, but you believe me, at least temporarily. Okay? You're willing to suspend your disbelief long enough to see if it's correct, okay? So now we made the problem bigger, but we have a constraint that we have to deal with. Now we relax the constraint, okay, to solve an approximate problem with this thing here, okay? So this is going to be x hat, v hat, but the problem here is that x hat is not really going to equal v hat, okay? So that brings us, so this is like, I'll call this like 1, 2, this is 3. This is beautiful stuff, by the way. 4, okay? So here is the beautiful thing, okay? Well, it's actually not quite beautiful yet, but it's very close to beautiful. Argmin over xv. So what you do is this, you take f of x plus h of v plus a over 2 x minus v minus u. It's either minus or plus. I mean, either way will work. It's just that I have to remember what my convention is. It's plus. Squared. Now, okay, when you solve this problem, it's going to give you a different answer for every u, right? Now, what the U does is it's like it preloads the spring. So what will end up happening is that, like so if this is the axis, let's say this is x minus v, okay? It's the difference between x and v. Well, this spring, when U is 0, this spring would be like this, right? Right? But if U is not 0, what will end up happening is that it will, let's say U is positive. Then what will happen is that your spring would do this. And this value here is minus U. Does that make sense? This is a really important idea, so let's spend some time on it because it could be very confusing. Let's look at this term here. This term is penalizing U minus, x minus v, right? But when this is 0, the energy is still U squared, okay? So even at 0, there's some energy. If x minus v is minus U, then this will be 0, right? So at minus U, then the energy associated with the term x minus v is 0. Let's think about that again, because it's really important, because you're going to get confused. Believe me, it's like super simple now, and then in 5 minutes you won't have any idea what the hell we're doing, okay? You'll be like, what happened? I thought he was trying to like thread the core of a nuclear reactor with, I don't know, with a toothpick, okay? So let's go and think about it again. This term here represents a spring. But instead of the spring just being like a spring that's set up so that when you let go of it, the two ends line up, it's set so it has some offset. And the offset is actually negative U. So the spring's designed. So here's the thing. This spring is preloaded. So you could preload the spring if you are omnipotent. You can preload the spring with some specific value of U, which ensures that at the solution to the unconstrained optimization problem, the values of x and v come out to be equal. In other words, you preload this. So what happens is that you let the problem solve, okay? It comes out like this, right? This is x and that's v. And you're like, well, that's not good because they're not equal. So you preload the spring to push this, like that, okay? Like you do what any good engineer would do, right? You take the screwdriver and you go, okay, you turn the little knob, the adjustment knob, so you go, to push them together, okay? And then you resolve the optimization problem, okay? But in any case, there's some position of that little, I like to think of U as like a little screw that I adjust, okay? You can adjust that screw until the two outcomes come out the same, right? For some value of U, this will produce the correct value. So this will equal to x hat v hat for some U. We don't know what U, but for some U, x hat will equal v hat, right? This is called the Augmented Lagrangian. This is called the Augmented Lagrangian. It's very closely related to the Lagrange Multiplier. Now, if you dig deep into the you know, like this, Halloween is appropriate now because you're like thinking back into the nightmares of your undergraduate education and constrained optimization. You probably remember doing the Lagrange multiplier at some point. If you're like most people, which would include me, that was a slightly terrifying experience because you did this crazy problems and you're like, I really don't understand what I'm doing here. And you get an answer and then thank God you get it correct, you get an A on the test, okay? But you didn't really understand what you were doing. Lagrange multipliers are actually a very beautiful concept, okay? but I won't go into them. But the point is that this turns out to be just like a Lagrange multiplier. It maps directly, if you read the notes. And the reason is if you expand this, you get x minus v plus u transpose x minus v plus u, right? So that's equal to x minus v norm squared plus 2 or minus 2 u transpose x minus v plus the norm of u squared. And since there's an a over 2 here, this is equal to a over 2. This is a over 2. Oh, yeah, so the 2 cancels out there, I guess. And this is plus a over 2. Is that correct? I think. So this is a. So it turns out this thing is the Lagrange multiplier. So lambda is a u. This is the Lagrange multiplier. Okay, that's the Lagrange multiplier. The Lagrange, if you recall, the Lagrange multiplier is the way you solve constraint optimization problems. The problem with the Lagrange multiplier is that when you did Lagrange multipliers in your undergraduate or whatever math classes, you always write these equations down well, actually, usually you don't solve them as optimizations. Well, no, you solve them as optimization. You differentiate it, okay? But the bottom line is this, that usually the way you solve for the Lagrange multipliers, you usually just kind of keep pushing the mathematics around, and then hopefully some magical thing pops out, and it tells you what the Lagrange multiplier is supposed to be equal to. But there really isn't a systematic way of picking the Lagrange multiplier, okay? It just happens, and by coincidence, your professors in your courses always give you problems where it works out very nicely. Okay? Okay? So, but the problem with the Lagrange multipliers is they're not really well adapted to solving computational problems. Because it's not an algorithm. It's really it's a kind of a mathematical technique. Yes?
Is A not a Lagrange multiplier?
A is not the Lagrange multiplier. The Lagrange multiplier is really A times U.
Does A have a special name? Because when we go from 2 to 3, we have a constraint, and then we make the constraint part of our loss function, which looks like the Lagrange multiplier. But I don't know.
It's very closely related to the Lagrange multiplier. The reason A is not a Lagrange multiplier is because when you, I don't want to get off too much into the tangent of Lagrange multipliers because the course isn't about Lagrange multipliers. Although it's important Lagrange multipliers, so it's worth spending some time on. But when you solve a Lagrange multiplying problem, you're doing the minimum over f of x. This is different f's and g's, so this is a separate box, okay? Subject to a constraint that g of x equals 0, okay? Right, so the way you end up doing that is you say the minimum over f of x plus lambda transpose times g of x. You minimize that, okay? So if you differentiate it, then you get the gradient of f of x plus lambda transpose times the gradient of g of x equals 0, okay? So this is the Lagrange multiplier because this is the thing you're multiplying. The thing you're trying to constrain is that x equals v. So that's like saying, so your function is that x minus v equals 0. Maybe I should have used a letter other than x here, because x represents x and v together. Yeah. You get it? So that's why that's not the Lagrange multiplier, because it's not multiplying the thing that's constrained to be 0.
I guess.
Well, it is multiplying the thing that's constrained to be 0, but yeah, okay, I know what you're thinking, but it's not right. Okay, because the problem is that with the Lagrange multiplier, the surface g of x I don't want to get into too much detail because I'll confuse everybody. It represents a manifold, okay? Okay, and the idea is supposed to be that G is like, it's better than I not try to explain this because I think I'll confuse everybody, okay? Okay, but this isn't the Lagrange multiplier, okay? Maybe there's some sort of interpretation where it is, but on the normal conventional viewpoint, this is not the Lagrange multiplier. The Lagrange multiplier is A times U, okay? But what ends up happening is that we have this additional term here, x minus v. So the interpretation is this. The Lagrange multiplier, the interpretation of a Lagrange multiplier is it's the force you apply in order to meet the constraint, okay? It's like you have a force in this high-dimensional space that pushes your variables in the direction to meet the constraint. But what you're saying is, okay, I can do that, but that's hard. It's better if I have a spring to hold the pieces together, okay? And then I push on it to meet the constraint. Does that make sense? In other words, it's like when you're trying to solve this problem, you don't want to do it as okay. Let me say it another one. I don't want to erase any of this honestly because this is all good. Let me just keep the story simple and say it like this. You have two terms here. You have the quadratic term, and then you have this u term that leads the offset. The offset zeroes you in by bringing the two terms together. But the quadratic term puts you in the right range by not letting the values get too far apart. Okay? The problem with Lagrange multipliers is that they're not really numerical algorithms you can solve on a computer. It's a method usually people use analytically on a piece of paper. Okay? If you want to generalize that method to use on a computer, you use Augmented Lagrangian, which is this. And I'm going to tell you why next, okay? Because we're very close to the punchline. Okay, so that's 1, 2, 3, 4. There's a step 5, okay? The step 5 is how do you pick U? That's the one thing I haven't told you yet. How do you pick U? I sort of suggested it when I gave you the physical analogy, that you have some sort of machine, the thing goes into some position, then you turn the screw until the two things come together, okay? And then you turn the machine on again. And now they're not going to be in the right position. So you turn the screw again to align them up. You can see an iterative algorithm here, okay? Okay, it's sort of physically intuitive, okay? And the place to put, so if you solve this optimization problem and x doesn't come out to be equal to v, right? So let's say x minus v equals, I don't know, 2, okay? So x is greater than v. Well, what's the logical thing to do with u? Just from a purely engineering perspective, just as a hack. Set it to 2 and try again, right? Because then you'll be like, oh, the two things came over here, so I'll apply enough force so that they go to here, and then I'll turn the machine on, the defractionation machine, and go, and it comes out, and oh, I got to adjust it again. And you see what I'm saying? I know it's weird. The sound effects help for me, at least, okay? That you have this defractionation machine that minimizes with respect to x and v, okay? When the machine produces its solution, the values are not correct. So you adjust the screw until you line the two pieces up again. And then you return on the defractionation machine, okay? And you repeat. And hopefully, if you do this enough time, if you're adjusting the carburetor on a lawnmower, it works usually, okay? You know, you start it up, it's too rich, it's too lean, you back it off a half a turn, you know? You do it again. How many people here have ever had to like adjust a lawnmower? It's a good life experience, really. Okay, so that's basically what you're doing. Now, I just need a little bit more space. So here's the algorithm. Unfortunately, I don't have quite as much room as I'd like, but I want to keep it all up here. 5. So you do this, repeat. Repeat. I don't know how to spell repeat. Okay? What's the first thing you do? The first thing you do is you solve this optimization problem, okay? Well, first of all, you initialize it with u equals 0, because you start off with you don't know what you have to do with the spring. So you start off with the spring being just like unbiased, okay? Like you don't know whether x is going to be bigger than v, or so you don't worry about it, okay? Then you say, okay, x. Oh, everybody knows the difference between pseudocode notation versus the arrow means assignment, okay? So they have arg min over f of x plus h of v plus a over 2 norm of x minus v plus u squared, right? Correct? But now the problem is x and v are not going to come out the same. So what you do is you say, okay, u I'll update by making it equal to the old u plus x minus v. Does that make sense? No? Do you have a question? Do you want to ask a question?
Why not just x minus v? That makes more sense.
Oh, that's a really good question. Because what's happened is that maybe my physical analogy wasn't perfect, okay? Okay, so the points came out like this, okay? And now there's like, on the lawnmower, there's a tension spring with like a long thing, and you adjust this, okay, to control the overall force, okay? And so you apply enough additional force to move it back. But you add that to the previous force. In other words, when you take the screw on the carburetor that you're adjusting, you start from where you were and you change it. Did that make? Of course, the true answer to your question is I'm going to drive a bunch of really complicated equations, and it's going to come out that it's true, okay? But I don't really want to give you that answer because it's not satisfying, okay? I'm trying to give you the intuitive answer. The intuitive answer is that u represents the additional force you're applying. The other way of looking at it is that the way you can produce this shift, okay, is if you have a function which looks like quadratic, okay, and then you add a function to it which looks like this, okay, what ends up happening is you get a function which looks like this. So the way you actually achieve the motion of the position of that minimum is by applying, putting the whole thing, applying a constant force, right? So this is a tilt, an energy landscape that looks like this. The force would be the derivative. So this would be a constant force, okay? To the left or the right in order to bring the two things into alignment. So you have to, the tilt of this plane, you adjust. You don't start from 0. Whatever tilt, you solve the problem, you got an x and a v based upon the u you had, and now you adjust the u based upon, you don't start from scratch. Did I explain that? I'm not sure it was the clearest, honestly. But so the first time you agree, because your concern is the fact that you're adding it to the existing u, right? But then the second time through, you don't want to start from 0 again. You want to start from where you were the last iteration. So you increment it to the previous value of u. Maybe that's the clearest way of saying it. Does that make sense to anybody? Maybe at this point you're just agreeing with me.
So essentially it's just like an experienced operator turn. You know that the car is turning, or the car is supposed to turn a certain way, but your wheels fucked up. So you turn it slightly better each time.
Yes, it's like a closed loop control system, right? It's like the thing was, it was like that's exactly what it is. Like the car's turning this way, so you actually, this happened to me recently because my car needed to be realigned, okay? And I was driving to Pittsburgh, and the car kept drifting to the left, and it was like, and so I brought it in because I had to keep pushing this way to keep the car from going to the left, right? Have you ever had that happen? Yeah. So as the car drifts more and more, you keep putting in more of a vice term to keep it going straight, right? It's also like when you bowl. I'm really terrible at bowling. So when you bowl it, you feel like if you go like that, it'll make the ball go that way, but it doesn't usually help that much. But the thing is that, so this is like you're pushing it the other way, okay? Yeah?
To me, it almost seems like with adding it, it's pushing it that same way, because like if x is greater than 3, we're setting u equal to u.
Yeah, it does feel that, which is why I spend a lot of time staring at the sign. Here's the way of thinking about it. That this u is muscling out x and v. Like, it's like x and v are in line at Starbucks, and u gets in and kind of pushes them out of the way, okay? So, because if you increase u, then it forces x and v, u and x and v, so if I put a parentheses around there, I call it delta. U and delta are competing because they're both driving the energy function up together. So if one becomes larger, the other one wants to become smaller. So by making u bigger, it forces x minus v to become smaller.
So it's kind of taking on the value that they were doing. So if x minus v was 2, you're trying to take away that effort that x and v are doing by adding in the 2.
Yes, that's precisely correct. And you know what? You may feel like we spent a lot of time on this, but honestly, this is way more important. Once you understand this, all the complicated equations in chapter whatever it is, chapter 8, 9, all the complicated equations in chapter 9 will be simple once you understand this intuition. Okay? So let's go through. There's actually one more step, but it only comes much later in the chapter. This is called the Augmented Lagrangian, okay? Then there's one other thing that's called ADMM, Alternating Method of Multipliers. Alternating Method of Multipliers is just one more step that's very interesting. What happens is that you break this optimization up into two alternating optimizations, one over x and then the second over v. And then from an engineering perspective, you'd say, well, of course, it's fine. But a mathematician looks at it and says, hold on for a second, that's not the same algorithm, okay? It turns out that both algorithms you can prove converge, okay, for convex functions. And so the second thing is sort of one step beyond this, okay? But let's just worry about this first, because once you got this in your head, the ADMM thing then makes a lot more sense, okay? So let's go through it one more time, because it's really important. Okay, you're trying to solve this minimization of the sum of two functions. You do this crazy thing where you split the two variables. This is called variable splitting. You split the two variables into two separate variables, x and v. And you do an unconstrained optimization over x and v, but that will give you the wrong answer. So therefore, you have to impose a constraint that they have to be equal. So now you've got a simple problem. You made it much more complicated and difficult. Seems like a bad idea, okay? Then you say, okay, well, on our road back to whatever, the road to something or other, isn't there a road to something where you end up better? Okay, in the road to better things, okay? Then we add this term over here that helps the two variables reconcile. Like, you know, they're like, okay, let's get together and try to be more similar, okay? But that doesn't give you the right answer. So then you add this u term, which tries to encourage them. This u term is like a marriage counselor, okay? It's trying to bring together the two parties to be equal, okay? Okay? So then what you say is, okay, well, how is that going to work? How do I find u? Well, this is the algorithm that does it. It goes, first you compute x and v, and then you take the difference between x and v, and you increase u by that amount with each iteration. Now what we're going to prove is that this algorithm converges when f and h are convex functions. By the way, and they don't have to be continuously differentiable. So, and this is called, well, they have to be convex functions, and the global minimum has to exist. Obviously, if the global minimum doesn't exist, it's not going to work. So, and this is, and the interpretation is that you can prove convergence of this thing by having this kind of dual space interpretation. Okay, and then I'm going to use this as an excuse to teach you a little bit about the theory of constrained optimization. But then when we're finished with this, this is really just a step along the path. Because what we're really interested in is the ADMM algorithm. That's the thing that's really useful. And the ADMM algorithm we're going to get by taking an additional step, okay, which I won't go into now. But read the notes now that you have this intuition, and then that will be helpful. Yes?
Why do you initialize v as well to be 0?
Well, you can initialize them to anything, and it will always, the convergence proof is independent of the initialization. But as a practical matter, like if you, very often in a real application, you might know what, see, the initialization doesn't even matter here because I just put argmin. In practice, this thing here would have to be some optimization algorithm. And you wouldn't actually achieve the global minimum. Otherwise, this would be a nested loop of infinite loops, which doesn't work out well. If each step requires an infinite amount of time, the algorithm is useless, right? So in practice, what usually happens is that this is an oversimplification because you usually have an optimization algorithm where you do give it an initial condition. And the details of how you do that initialization are important, and I don't usually talk about them in this class, but I'll be happy to cover it. But so what I'm really saying is this theoretical algorithm that a mathematician would think about doesn't depend on any initialization of u and v. It doesn't matter. In practice, from an engineering point of view, when you go to implement it, you really do have to have some initialization. And often there's some kind of v equals x init. There's usually some kind of intuition in your problem that there's some reasonable initialization. But that's not a sort of a general methodology. It can vary from application to application. Okay? Good. I'm sorry I got to go because I have